So, welcome back. We have been looking at binary relations, and there is no other place where binary relations are so much in existence as in a family database essentially. So, let us talk about trying to see how, if you wanted to create a database of your family uh, which told you how someone is related to somebody else, then how could we build that essentially. So, you have relatives like uncle, aunt, grandma, brother, sister, cousin and so on. How can we go around representing such knowledge or such information? Indian languages in particular are rich in specific names for relations. So, while in English you might say aunt or uncle, in Indian languages we have a name for every specific kind of an uncle. So, there is chacha, there is nana, there is nani, mama, mamera bhai and so on. So, many of you would be familiar with such relations. All Indian languages are rich in these terms. We can define some basic relations which we will store in the knowledge base, and then we can infer the other relations from there by defining the connections between basic relations and the derived relations. So, for example, you might want to add the fact that Aman is the chacha of Vaishali. So, chacha means father's brother. Vaishali's brother is Aman. So, should we add them to the knowledge base or should we infer them as and when needed essentially? So, that would take us back to the original debate that we had about whether forward chaining is better or whether backward chaining is better. If you do forward chaining, then you will keep adding new facts to your knowledge base. You may or may not need them or use them, and they will take up space, but query answering would be very quick because the thing would be there in your knowledge base. Backward chaining on the other hand is lazy, and you will only make the inferences when you need to make them, which means that query answering would take a little bit of time, but the knowledge base would be compact. So, there are trade offs obviously. Now, one thing we have to be careful of when we represent things like family databases, and in general when we talk about knowledge about people, we have said very happily that Aman is the chacha of Vaishali, but in the real world there may be many people of the same name essentially. So, there may be many Amans and there may be many Vaishalis. Which one is the one that we are referring to? How do we know which individual the constant symbol we are using in our knowledge base maps onto in the domain? Because in the domain many people would have the same name. We often try to address this problem by using surnames or village names, as the convention may be in different parts of the world, but the problem persists because you always have people with the same name and the same surname. There are many instances of that. So, one idea is to use suffixes of some kind to distinguish between individuals. So, you might say Aman 21 is one individual, Aman 39 is another individual, and then of course, in the knowledge base you can add the relevant facts. You can say, for example, Aman 21 is the chacha of Vaishali 33 or something like that, and then you know that you are talking about the right people. This is the idea that was proposed by Charniak and McDermott in their book on artificial intelligence, which was published in the mid 80s. Nowadays, you might use something like a uniform resource identifier. I encourage you to go to this site, but when we look at RDF and OWL, we will talk about these things again later. So, we said that we will define a family database or knowledge base in terms of the primitive relations. So, what would be the input to this whole thing is some primitive relations, and the rest of the relations would be defined in terms of those primitive relations. So, what is the bare minimum that one can work with? So, let us say that we begin with the following set of primitive relations. One is the parent relation, and here we read this as parent x is a parent of y. Now, I have said this earlier also that when you write parent x y, it is not clear to us as to whether x is a parent of y or whether y is a parent of x, because it is just a formal agreement between us essentially. Language of course tries to solve this problem by expressing things using linguistic connectives. So, Suresh is the parent of Manish. So, we already know that Suresh is the parent of Manish and so on. So, in all languages there are case markers which tell you how what case that each individual in the sentence takes. When we do things in logic, we have to make these things explicitly in some way or the other. So, one way would be to use something like a schema which is used by the database community, that they say that when you say the parent relationship, the first argument is the parent and the second argument is the child essentially. We could use this itself because we have just said that variables are going to be capitalized. So, it helps in specifying what is it that you are talking about. The other primitives that we need is gender information. So, we have two predicates here, male x which says x is a male, female x which says that x is a female. If there are only two genders, we could even do away with one and have a rule somewhere that if you are not a male then you must be a female, but that is kind of becoming a little bit too compact if you want to say that. Notice that in these relations we are not saying man woman. When you talked about married, we said man woman because that is when we said that it is humans who get married, but these relations would apply to any living creatures. So, we could define the rest of the terms in terms of these predicates. So, for example, we can define son as saying the first argument is the second son of the second argument. This is different from what we had said earlier, which is why I keep repeating that you could use both, but you must be consistent and you must be clear as to what your representation means essentially. So, one way to do is to define it as a schema essentially. So, we can define son now as saying that son is the son of the parent. There is a little bit of overloading of symbols there. If parent is the parent of the son and the son is male essentially. So, only this parent and male related relation we have used here to define son. You can define other things equally. So, I am using x y from henceforth, easier to read. So, we say x is the mother of y if x is the parent of y and x is female. Then we can define our earlier definition that we had using equality. X is equal to the mother of y is equivalent to saying mother x y. So, the next thing one would talk about is siblings. If two people have the same parent, then they are siblings essentially. So, let us follow that definition and let us adopt that definition. That can be expressed as saying that for all y z, z is a sibling of y is equivalent to saying that there exists an x such that x is a parent of y and x is a parent of z. So, the same x is the parent of both y and z, then z and y are siblings. Now, if you look at this definition carefully, this will allow you to say that Suresh is the sibling of Suresh. You most likely do not want to say that. So, if you do not want to add that in your, or if you do not want to be able to infer that in your knowledge base, then you must add another clause to that, which is that z is a sibling of y if z is not equal to y and there exists an x such that x is a parent of y and x is a parent of z. So, that would make it more consistent with what is our notion of what is mean to say that one is a sibling. Now, the sibling relation should be symmetric. So, you should add these facts to your knowledge base that and it is transitive. So, that should also be added. So, that if x is a sibling of y and y is a sibling of z, then x is a sibling of z as well. This transitive relation maybe one wants to be a little bit more careful with, because it could be possible that x and y have one parent and y and z have a different parent. So, then they are not technically speaking siblings, but one has to be maybe a little bit more careful in defining the transitive relation. We can define sisters and brothers. A sister is a sibling who is a female and a brother is a sibling who is a male essentially. Then we come to aunts, I think. A is an aunt of x if there exists a P who is a parent of x and a sibling of A. So, we can define it as follows, that for all A, for all x, A is an aunt of x is equivalent to saying that there exists a P such that P is a parent of x and P is a sibling of A or A is a sibling of B, that is a symmetric relation, and A is a female. Now, since this is an equivalence relation, we can break it down into two directions. We will do that, but before that I would urge you to define Chacha. We already said is father's brother, and Chachi which says father's brother's spouse. So, let us look at two sides of the implication. If you go from left to right, then you are saying that if A is an aunt of x, then there exists a P such that P is a parent of x and P is a sibling of A and A is a female. So, you would now remember that here this P is a Skolem function. So, we are only defining a relation between A and x, and suddenly this P has come into between, and this P is of course related to A and x, and that is why it should be a Skolem function of both A and x. If you were to Skolemize it, the right to left reads normally. So, we have this there exists P inside the antecedent, and we have already discussed this, that we can, when we move this out, it becomes a universal quantifier. So, an existential quantifier in the antecedent can be seen as a universal quantifier, and you can write it as a universal quantifier. So, the reading of this statement, which is a universal statement, says that for all P, for all A and for all x and for all P, if P is a parent of x and A is a sibling of P and A is female, then A is the aunt of x. So, everything is a universal variable here. The following would not be accurate, that if we simply said for all A, for all x, for all P, aunt A x is equivalent to those three facts that we were talking about. And to verify that, you should look at the implication from the left to the right. What does it mean if we were to say that essentially? So, for one thing, it would say that for all P, P is a parent of x. Now, you do not want to assert something like that. Okay, so let us move a little bit further away into the family. Let us talk about cousins and grandparents. G is a grandparent of x if there exists a P who is a parent of x and a child of G. So, which we can write in a very simple fashion, that for all G, for all x, grandparent G X is equivalent to saying that there exists a P. P is a parent of X and G is the parent of P essentially. Remember that this X and G are still universally quantified for all G, for all X. So, as an exercise, please define Dadi, which is father's mother, and Nani, which is mother's mother. These would be special cases of grandparents, and we can define relations between Dadi and grandparent also. So, we can say a Dadi is a grandparent where the grandparent is a female and the parent is a male essentially. So, you could do that, or you could define it from first principles in terms of father and mother essentially. We say that two individuals V and W, for all V W, we say V is a cousin of W if there exists X and Y such that X is a parent of V and Y is a parent of W and sibling X Y. Sometimes we refer to this as the first cousin in many societies. One question I would like to leave you with is, does the definition of cousins here include the definition of sibling? So, are siblings also cousins or are they not, according to the definition that we have written here? So, please go back and check that and see whether they are included or not included. How would you generalize to second order cousins? So, second order cousins would be whose parents are cousins and so on. And you could even do a generalized cousin relation, which basically includes first cousins, second cousins, third cousins and all kinds of cousins into one category called cousin essentially. So, if you say that X is a cousin of Y, then essentially it will boil down to saying that both of them have a common ancestor. So, now we need to define ancestor, but we will do that in the next session after a short break.